This tutorial shows you how to use a geographic information system known as GRASS GIS to make rasters from vectors. This is an important skill for ecologists. For instance, the species distribution modeling software Maxent requires environmental data in the form of rasters only, not vectors. This conversion requires the user to carefully consider the resolution that they want the raster to have, as well as which data they want to rasterize. Vectors can hold multiple attributes simultaneously, whereas rasters can hold only one. For more information on GIS, and on GRASS GIS in particular, see the links in the show notes below. This tutorial assumes that you have GRASS GIS installed. Instructions can be found in the show notes below. This tutorial assumes you are using Ubuntu Linux version 20.04 as your operating system. If you do not have Linux, you can emulate it on your Windows or Mac computer for free. See the show notes for details. In fact, I am emulating Linux right now on my Mac computer using VirtualBox. I have a VirtualBox virtual machine pre-configured with the software I will show you today, as well as other population genetics and ecological niche modeling and GIS software. See the show notes below for step-by-step instructions to download and hook up this virtual machine within your Windows or Mac computer. Let's go ahead and get started. The first thing you want to do is open up a web browser such as I have pinned to my favorites on the left. Navigate to my website, joshbanta.com. Click on Tutorials. Type Control F to open up a search window. Type Making Rasters from Vectors. There's only one tutorial in my list to worry about, so you can click on it. Next, click on Files Needed for Tutorial. You don't have to wait for this preview to open. You can just click this download icon. Click Download Anyway. When the download is finished, you can close your Chrome or other internet browser. Next, click on File Explorer, which I have pinned to my favorites on the left, or which you can find by searching below. Navigate to your Downloads folder. Click the file that we just downloaded, Making rastersfiles.zip. This opens up a program called Archive Manager, which shows us the contents of the compressed zip archive that we downloaded. These files cannot be used within the zip archive. They have to be extracted to another location. To do that, come back to File Explorer. Click on your desktop, and then from the word Desktop, click on the drop-down arrow and select New Folder. Let's call the new folder Making Rasters. Click on Create. Now, come back to your Archive Manager program. Click on the first item in the list. You can skip this one that says Mac OS. Then take your mouse down to the bottom. Then hit the Shift key and then regular click. This highlights all of the items within the compressed archive. Now, regular click on one of the icons, any one of the icons within the compressed archive. Make sure that everything remains highlighted, and drag all of those files into the Making Rasters folder onto your desktop. When completed, you can close your Archive Manager program. You can also close your File Explorer. Next, open up a terminal window, which I have pinned to my favorites on the left, or which you can find by searching below. Begin GRASS by typing GRASS. Now, the first thing to do is to make sure that your GRASS GIS database directory is set to your GRASS data folder within your home directory. My home directory is named Sample. If you do not have a GRASS data folder within your home directory, be sure to create one. And you can get to that by clicking on Browse and then clicking on Home, and then clicking on GRASS Data, and then clicking on Open. So be sure that your GIS database directory is set as such. Next, click on New to start a new GRASS location. To be sure that this GRASS location does not interfere with any GRASS locations you've created in other tutorials, I'm going to call this one Projection 30. Click on Next. Click on Read Projection and Datum Terms from a georeference data file. After clicking Next, click on Browse. Navigate to your desktop and double-click on the Making Rasters folder. Find the file called Merged Soil Layer Columns T_fixed.shp. This is soil data about the different soil types across the United States. When you have a series of files that end in DBF, LYR, PRJ, SBN, SBX, SHP, and SHX, always select the one that says .shp. This multiple files format is colloquially known as the Esri shapefile format. This is a very common GIS format that is used by many different programs, including GRASS GIS, which can import and export in this multi-files type. This multi-files type is exclusively for vector data in the form of points, lines, or polygons. Click on Open. Click on Next. Now click on Finish. Click on OK. Do you want to import this layer to the newly created location? Click on Yes. We have a spinning wheel indicating that GRASS GIS is working, as in the middle of a computational process, and so we have to wait. This was a large file we were setting up, so it took several minutes for GRASS GIS to complete the process. We know it is finished when this dialog window opens that says that the data file was imported successfully. Click on OK. Now click on Start GRASS Session. We have set up our new GRASS location, and we have imported our soils layer. We cannot see the soils layer, however, because it is not yet placed in the table of contents. To do that, we go to File, Map Display, Add Vector. And then we select the soils layer from the drop-down menu and click OK. We see that we have the spinning wheel, meaning that GRASS GIS is in the process of taking care of our request and is not yet finished. After not too long, you will see the soils layer in your map display window. To see it at its full extent, right-click on the soils layer in your table of contents if you are on a Windows machine, or if you are on a Mac laptop, push down on the trackpad with 2 fingers and select Zoom to selected maps. This is a big shapefile, so this process takes a little while. As you can see, the process is still underway. Now we can see the soils layer at the extent of the entire United States. Before we move on, I want to show you something. This is a quick splice to ask you to consider subscribing to my channel by hitting the subscribe button. It does not cost anything. It is totally free. But if you like what I am doing and want to support my work, I encourage you to visit patreon.com/joshbanta and make a voluntary contribution. The link is in the show notes below. Your support helps me to deliver new content and keep this channel current and vibrant. Thank you. We're going to look at the ellipsoid, projection, and datum of our current GRASS location. So go to Settings, Computational Region, Show Current Region. The datum is North American datum 1927. The ellipsoid, which goes along with 1927, is Clark 66. And the projection is Albers equal area, which typically goes with the NAD 1927 datum and the Clark 66 ellipsoid. But what are the units of measurement? In other words, what are the units of distance for this GRASS location? That information is not provided here. The way to find that location is to go back to the original GRASS layers that we imported. So open up File Explorer, which I have pinned to my left. Navigate to your desktop, click on Making Rasters. From this set of files that comprise the shapefiles format, this file here, which has the extension .prj, contains that information with the units. Right-click on it if you are on a Windows machine, or if you have a Windows-style mouse. If you are on a Mac laptop, push down on the trackpad with 2 fingers and select Open with Other Application. Click View All Applications and scroll down to Text Edit. Select it and click the Select button. It's not written here in the most user-friendly format, but if you look here at the end, it says that the unit is in meters. You can go ahead and close the Text Edit program. And you can go ahead and close File Explorer. We're getting ready to make our raster momentarily, but before we do that, we have to set the resolution for the raster that we will create. To do that, go to Settings, Computational Region, and select Set Region from the drop-down menu. First, click the Resolution tab. Then, in the 2D Grid Resolution box, type in 1000. Think about this. What does the 1000 refer to? This refers to the raster having grid cells that are 1000 by 1000 in size. What are the units? That is for you to think about. Now click on the tab that says Bounds. Click the button that says Align Region to Resolution. Click on Run. When finished, click on Close. We are ready to make our raster from a vector. Click on Vector, Map Type Conversions, Vector to Raster Data. For the name of the output raster map we are going to create, we're going to call it CEC. That stands for the cation exchange capacity of the soil. For the source of raster values, we select attribute. Now this is an important point. When we're making our rasters, the data could be in the form of numeric data. So for instance, the cation exchange capacity ranges within a certain range of numbers, but those numbers within that range can take on any value. By comparison, there are non-numeric data sources. For instance, the type of soil. Is it an alpha sol? Is it a sand? Is it a clay? Those are not numeric. Those are categories. Now, you can have categorical data that's coded as numbers. So you could have alpha sols as 1, sands as 2, and clays as 3. But that would still be categorical data because there's no sense in which the number 2 in that example is greater than the number 3. That we've just coded our categories as numbers. But with cation exchange capacity, a higher number for the cation exchange capacity
to ask you to consider
cation
subscribing to my
exchange
channel
capacity.
by hitting the
It's
subscribe
numeric.
button. It does not cost anything.
So
It
in
is
that
totally
case,
free.
from the source of
But
raster values,
if
we
you
choose
like what I am doing
ATTR for
and
attribute.
want to support my work, I encourage you to visit patreon.com/joshbanta and make a voluntary
Click on the
contribution.
Attributes tab.
The link is in the show notes below.
And it says
Your
here,
support
name
helps
of
me to deliver
column
new
for the
content and keep this
ATTR
channel
parameter.
current and vibrant.
Data type
Thank
must
you.
be numeric. Because we selected ATTR, from here we select the column that has the numeric information that we need. So we come down here to fixed CEC, which stands for fixed cation exchange capacity. There's other variables here like the percentage of clay, the available water content, the depth to the seasonally high water table. Oh, that's this one here. This is the bulk density. A bunch of different factors that have to do with the soil. So let me explain. And what I'm going to show you in this moment, you do not need to have in your recording of yourself doing this laboratory exercise. So if I zoom in here on some region of the graph, of the map, this is vector data. So we have a bunch of polygons. Within any one of these polygons, there is a particular soil type with all of this information for that soil type. So if we query it, we find that that particular locale defined by that polygon is all the same soil type. That's why it's a single polygon. And within that polygon, we have all of the information about it. So the depth to the seasonally high water table is 0. So this is an area that floods. The available water capacity of the soil is 0.12. The cation exchange capacity of this particular polygon, of the soil for this particular polygon, is 6.126. The percentage of clay for this particular polygon is 21.8%, for instance. So that's all of the attributes for this particular polygon. But if we're turning this from vector data in the form of polygons to a raster, we're going to be converting this data in the form of polygons into essentially an image, like a digital image or like your TV screen, which is made up of pixels. where every pixel has a single number in it. So we have to choose some attribute from among all of these attributes to cover our entire image with, where every pixel will have just that attribute for that particular locale in the landscape. So by turning this vector into a raster, we're going to break up these polygons into individual grid cells. And each individual grid cell will have one number in it, corresponding to whatever attribute we choose. In our case, we will be choosing cation exchange capacity. So all of these polygons will be broken up into little grid cells, and in every grid cell, the cation exchange capacity of that grid cell will be computed based upon the cation exchange capacity of the polygon from which that grid cell was derived. And if that grid cell overlaps two polygons, the polygon that covers most of that grid cell will be the polygon from which that grid cell inherits its attribute data. Now back to the tutorial. Now I want you to continue recording what you see me doing going forward. Click on Run. When the command is finished, you may close the dialog window. The map that you have open now on your screen, I'll uncheck the soil vectors layer so that now we just have this layer selected. This is a raster layer. And by the way, you can tell here by this icon is a raster icon as compared to this icon here, which is a vector icon. We can also tell that it's a raster layer if we zoom in enough. So I'm going to zoom in here. Oops. Select the zoom tool. I'm going to zoom in here. Zoom in some more. And you can see that this particular layer is made up of grid cells. And these grid cells, if you zoom in enough, are square. And every grid cell has an attribute that's color-coded here as a color. So every grid cell has a different color. The color scheme being used right now is not great. It's not giving us a very good distinction between the different grid cells. Let's not worry about that. So you've successfully converted your vector into a raster. And I'll just show you one more thing. I'm just going to zoom in again. And this time I'm just going to query some of these cells. So that you can see now there is just one value associated with any pixel in this entire map. So if I click on another location, I get a different value for every pixel, where these pixels inherited the attribute value of cation exchange capacity from the soil polygons from the vector map of soils from which we created our raster map. You don't need to do those zooms and querying the points for your recordings. So we have our raster, but for the purposes of this course, we're building towards doing species distribution modeling using the software Maxent. And the software Maxent requires you to use rasters in the ASCII file format, which, if you've done my tutorial on rasters, you already have some experience with. It's these simple text files where they store the attribute data in the form of text. So because we're building towards species distribution modeling, I now want to show you how to take this raster out of the GRASS GIS format and export it into the ASCII file format. Click on File. Then click on Export Raster Map and select Common Export Formats. For the name for the output raster file, click on Browse. Choose Desktop. It's very important that you choose Desktop from here and not from the sidebar over here. Double-click on Desktop. Double-click on Making Rasters. And then where it says Name, we're going to enter the name for the ASCII raster file that we're exporting. We'll call it cec.asc. Click on Save. Next, we have to change the raster data format to the ASCII file format, which is here, AAI grid. Next, and this is very important, under the Optional tab, check the box that says Force Raster Export despite any warnings of data loss. Also, under the Creation tab, select Float 64 from the drop-down menu. And under Assign a specified no data value to the output bands, type in -9999. That means all of the places within our image where there's no soil data, such as out here in the ocean, those pixels all get the value -9999, which most computer programs recognize means not to draw anything in those pixels. Click on Run. When the task is completed, you hit Close. Now we will look at the file that we have created. Open up File Explorer, which I have pinned to my favorites on the left. Navigate to your desktop, double-click on Making Rasters. Here's the file, cec.asc. Right-click if you are on a Windows machine or have a Windows-style mouse. Push down on the trackpad with 2 fingers if you're on a Mac laptop. And select Open with Text Editor. Please be patient as it will take a few minutes to load the very large file. This is a raster image that has 4,616 columns and 3,174 rows. This is the coordinate of the lower left corner on the x-axis over here. This is the coordinate of the lower left corner on the y-axis. I'm sorry, lower left corner on the x was over here. Lower left on the y is over here. The cell size is 1,000 meters by 1,000 meters for each grid cell. And the no data value as we set was -9999. Scroll down to some other place within this ASCII file where there's actual data. This way you can see that the whole file is not empty. So congratulations, you have successfully made the ASCII file version of the raster. You may close Text Editor and you may close your File Explorer. But we're not done. We're going to make another raster. This one will have a smaller spatial extent. Go to File, Import Vector Data, Simplified Import with Reprojection. We're going to be importing vector data, and I'll show you why. That is in a different projection, ellipsoid, and datum from the current GRASS location. Therefore, there are 2 ways that we could import this shapefile. We could import it by creating a new GRASS location that is tailor-made to that shapefile and importing the shapefile into that GRASS location and then reprojecting the file from that GRASS location into here. Or there's a shortcut that we've been using in the last couple of labs, which is to simply choose Simplified Vector Import with Reprojection, where the shapefile will be imported directly into our current GRASS location by transforming the data as it's being imported so that the data will match, and it'll be reprojected to match the current location's projection, datum, and ellipsoid. Click on Browse. Navigate to your desktop, double-click on Making Rasters, and choose Texas Eco i3.shp and click on Open. Now click on Import. It's reminding you that it's going to be reprojecting and transforming this data as it's being imported into this current GRASS location. So click on Import and Reproject. When it finishes, you can click on Close. Now you may be wondering, uh-oh, it didn't work. I don't see that new layer in the table of contents. And that's because GRASS GIS sometimes does not automatically add new layers to the table of contents, even though that they are now in the current GRASS location. And in order to show them and have them show up in the table of contents, you have to go to File, Map Display. In this case, it's a vector, so it's Add Vector. And from the drop-down menu, you'll see that it's there. We select it. We select OK. And there it is. And let's go ahead and zoom in on it. So this layer is from the Environmental Protection Agency, and it shows the ecoregions of Texas. The conversion of this vector into raster data will be different because the attribute data that we're going to rasterize is categorical rather than numeric. So each one of these ecoregions has a name, or maybe it's coded with some sort of a number, but it's not numeric in the sense that if this is region 4, it's not greater than region 3 in some sense. They're just numbers corresponding to these different categories. Or maybe these have names. Let's have a look. So I right-clicked on the layer, and that's on a Windows machine or with a Windows-style mouse. On a Mac laptop, you push down on the trackpad with 2 fingers, and you go to Show Attribute Data. And as you can see, these different ecoregions have names. So the process for making rasters on categorical data is different. So we're going to start by going to Vector, Map Type Conversions, Vector to Raster. And for the name for this output raster map that we will create, we'll just call it Texas Eco to keep it simple. And now under this drop-down menu for the source of raster values, we're going to select CAT, which stands for categorical. Click on the Attributes tab. But now, instead of selecting a column for the attribute parameter, since we're not doing numeric data and this is for numeric data, we're going to select the name of a column used as raster category labels. And in this case, we're going to use the column called CAT, standing for category. So just to show you, and you don't have to show this in your recording, I'm going to pull up the attribute table data again. There's this column here called category, called CAT, which has dummy variables for the ecoregions. And these dummy variables have the numbers 1 through 12. This is convenient because we can later decode our raster by coming back to this data table and seeing that any grid cell that has the value of 4, that corresponds to the southwestern tablelands. Something like that. So you want to start by making your raster use one of these columns that already has dummy variables in it. And if there isn't a column that already has dummy variables in it, you should add one. but that's beyond the scope of this tutorial. We already have a column with dummy variables. It's this column called cat. So what we're going to do is we come in here, and the name of the cat column used as a raster category labels is cat. And now we click on Run. When the process is finished, as you can see by the new raster image displaying on our screen, you can close the dialog window. And we can uncheck some of these other layers, which we're not currently using. And this looks very much like a raster. And if we zoom in, we'll see that we have the typical pixels. If we zoom in, you can see that things get blocky and that it's made up of pixels. And if we query any place on this map, there's a single value corresponding to that location. So this is number 9, category number 9. Over here, this is category number 6. So we're at the border of two different ecoregions. Each one of these pixels is in ecoregion 6. Each one of these pixels is in ecoregion 9. And just to remind you, and you don't need to pull up this attribute data table in your video, but just to show you. Oops, come here. So 9 is the Texas Blackhead Prairies. 8 is the Southern Texas Plains. We can easily go back from the raster attribute values to the names of those categories because we rasterized this numeric column. You can only the rasters will only store numeric data. So it's very important that you choose a column with dummy variables in the form of numbers to be turned into a raster. And I know I said that this is non-numeric data. It is non-numeric data. These numbers simply represent categories. So we have to trick GRASS GIS into making a raster out of them, even though it's categorical data. And we do that by rasterizing this column of dummy variables. Now, I want you to show me the steps that you learned. If you're watching this video on Canvas, those steps are from 24 minutes and 20 seconds until 28 minutes and 19 seconds. If you're watching this video on YouTube, those steps are 24 minutes and 49 seconds until 28 minutes and 48 seconds. And what I want you to do is to take these Texas ecoregions raster layer and turn it into an ASCII file. I want you to save it with a different file name, and I want you to go through all those steps, including the steps where at the end you opened up that ASCII text file and you showed me a different place within the text file where there was numbers besides -9999, where you showed me that there were other numbers within that text file, that the text file was not just empty. So I want you to go through and do that and record yourself doing those steps for the Texas ecoregions raster. And after you're done with that, you are finished with this lab.